Thank you. Thank you for giving me the chance to give a talk here. And this talk is about my thesis supervised by Pierre-Henri Chaudoir. First, let's see something between arithmetic and geometry. Suppose x0 is a projective, smooth, and geometrically connected curve defined over fq, a finite field. And f is a global function field with eta is the generic point of x0. And S0 is a finite set of closed points of x0. So equivalently, this is the finite set of places of f. And we have the fundamental group of this open curve. It's isomorphic to the Galois group of the here f bar S0 unramified means the maximal extension which are unramified outside S0. And so with this isomorphism, we know that an l-adic Galois representation, when I say l-adic, it means with killer-bar coefficient, which are outside, unramified outside S0, corresponds to an l-adic local system over the open curve x0 minus S0. And we denote the x by the base change from x0 to the algebraic to an algebraic closure of the finite field fq, and s also the base change from S0 to fq bar. And we denote fx with the Frobenius endomorphism of x. This by definition acts as identity on the second factor, and for the first factor it acts it sends a function to its q's power. And given a point S0, when we base change to the algebraic closed field, this point will split into these many points, depends on the residue field of the S0. And let S belong to, and we know that the Frobenius permutes cyclically on the set of these points. And let S belongs to the S, and which lying over S0. And we can form a scheme which is defined by this. And here, sorry, I made a mistake. This should be without star. XS without star is the Hanselization of X at S. And XS with star is this Hanselization minus S. So the same, you can, instead of Hanselization, you can take the completion. So this corresponds to the spectrum. This corresponds to the spectrum of maximal unramified extension of the local field. So we know that in the last line, the fundamental group at this spectrum is in fact, the inertial Galois group. So, and consider an l-adic local system over the open curve. And for each S, it induces an IS representation simply by pulling back to this spectrum. And so this IS inertial group representation is called local monodromy at S, and we denote its isomorphic class by RS. If, moreover, the local system is fixed by pulling back by the Frobenius, it means that this local system comes from a local system over the curve over the finite field. So we must have that the Frobenius pulling back the local monodromy at this point to the local monodromy at Rs. And this implies that Rs as a representation of, the first condition implies that Rs as a representation of IS0, because we have seen that for any point S lying over S0, the fundamental group is isomorphic to the inertial Galois group, which should be independent of the any point lying over S, but the isomorphism itself depends on the point S. So this representation, viewed as a representation of the inertial Galois group, should extend to a representation of the wave group. And it is a theorem of Grothendieck that if rho is an l-adic representation of this wave group, then the restriction of rho to this inertial group is quasi-unipotent. So if we denote this z hat p prime want to be this limit, I write 1 here because the Frobenius act on this side by multiplication by q. So here the limit, projected limit is taken for all n, which is prime to p. So we have a short exact sequence by the wild ramified Galois group and the inertial Galois group. And here, this is the timely ramified inertial group. And so if we consider a representation which is timely ramified, and so that it comes from a local monodromy of a local system satisfying this condition, then we know it's simply a representation of this group. And any quasi-unipotent representation of this group is of this form. Here, this is a direct sum, and the first is a character. The second is a unipotent representation, which I write which depends on the character. So this unipotent representation should factor through the quotient of l-adic integers of this ring. And chi here then is a character of this z hat prime. And it is after Drinfeld for rank 2 and Lafog for general rank, we have a bijection, which is a long lines correspondence. Between the pairs, where L is a irreducible l-adic local system over this curve of rank n with extra data j. Here j is isomorphism between the pullback of L with L itself. And this kind of data should correspond to bijectively to absolutely Caspita automorphic representation of GLNA. Here, absolutely Caspita means its space change in the sense of functionality from GLNA to GLNA tensors FQN remains Caspita. This is because the L itself here, it is not an irreducible l-adic local system over the curve of finite field, but it is irreducible over x minus s. So we need the base change from the Caspita representation should remains Caspita after base change from GLNA to GLNA tensors FQN. In fact, it should be remains Caspita here for any finite field extension. And I should mention that this bijection depends on auxiliary isomorphism from C to the isomorphism to the QL bar. And if you change another isomorphism, then this correspondence is different. And under this isomorphism, the ramified local components also correspond to each other in the sense of local long-length correspondence. And so if we start with an l-adic local system on x minus s, and so that there exists an isomorphism from fx star pullback L to L itself, then we can look at the monodromy at the point of S. And if, for example, it has trivial monodromy, then it means the inertial Galois group act as identity. So corresponding by long-length correspondence, it corresponds to unramified principal series representation. In fact, there are many unramified principal series representation. And another example is the local monodromy at point S is principal unipotent. It means that first, the representation factors through the timely ramified inertial group. And then this timely ramified inertial group maps to l-adic integer ZL. And we consider a morphism. Here, N is a nilpotent element with one Jordan block. And A maps to this exponential. Then this is a so-called principal unipotent. Because here we consider a continuous l-adic representation. So you can also consider the representation of the Lin Wei group. And using dictionary of local long-length correspondence, you see that this should correspond to an initial class of Sternberg representation. And so we want to consider a set, which is the set of irreducible l-adic local systems of rank n with local monodromy R fixed. And if we need to impose a condition that this monodromy set should be fixed by pullback of the Frobenius. So that with this condition, the Frobenius itself can act on this set by taking pullback. So we want to consider the fixed point of this action. In particular, its cardinality. So we denote CNK to be the cardinality of this set. And it is a theorem of Drinfeld. It considers the case that S0 is empty, and the genus of the curve is greater than or equal to 2. And then there exist Q-way numbers. Here, Q-way numbers are algebraic integers whose complex absolute value is a half power of Q. And for any embedding. And these Q-way numbers found by Drinfeld are monomials of eigenvalues of Frobenius endomorphism on the first Adala cohomology of the curve. And they are integers mi, so that C2k equals to this for any k. And in particular, these numbers doesn't depend on k. And here, Drinfeld's result is for genus G greater than 2, but for generous 1 or generous 0, this is just an empty set, so nothing to consider. And for concerning the question of calculating the cardinality of this set, there are some other results except this one, besides this one of Greenfield. And all of these results show that the cardinality here looks like the number of FQK points of a variety, because it is a theorem of l-adic and Deligne that a FQ number of a variety should be given by this kind of number. So they are a result of Deligne flicker. They impose, they suppose S0 has at least 2 points, and at each point they impose principal unipotent local monodromy. So in the automorphic set, they need to calculate the Casquito representations so that at 2 places they are initially equivalent to a Steinberg representation. And there is another result of flicker. He considered the case of n equals to 2 and with 1 point. And at this 1 point, he still impose principal unipotent monodromy. And there is a result of Aronkin. Here, Aronkin suppose that this set S0 is non-empty, and local monodromies are sums of characters with some additional requirements. These additional requirements comes from analogy from geometry. When people consider character variety, they will sometimes impose so-called monodromy of general position. And Aronkin consider the similar case of general position monodromies. And he also gives he also calculates the number of CNK in terms of indecomposable vector bundles. And there is a result of, I heard last week of Savin Templier, that if S0 is non-empty and at least one place they imposed the so-called MGS local monodromy, and all of these results, they show that there exist Q-way numbers so that the cardinality can be written in this form, except the first. The first I write here is just to indicate the dominant term, but the dimension of other results can be different. And my result is about S0 is still empty, and of course we impose the genus is greater than or equal to 2, otherwise it is an empty set to consider. Then there are Q-way numbers which are still monomials of eigenvalues of Frobenius anamorphism on this first cohomology of the curve. And there are integers mi so that this set can be written, the number can be written in this form for any k. And this term is the dominant term. Usually it gives you the information about the dimension of the variety, if there is any variety. So some information can be read from my calculations. First, these integers, mi, which usually means the multiplicity of the eigenvalues of Frobenius acting on the cohomology of a variety. And these mi depend only on the genus of the curve. It depends nothing else. Of course, on the rank n also. And this number is the half of the dimension of the modular space of rank n stable Higgs bundles on X0. And these Q-way numbers are essentially Q-way numbers of the modular space of stable Higgs bundles on X0, because they are result by Olivia Schiffman and Anton Bentley, who showed that for the modular space of stable Higgs bundles, because it is a variety, and its number can be also written as a form similar to this one. The first should be double of this, should be the square of this term, the dominant term. And here the Wei numbers are essentially the same with the Wei numbers of ours. And our method to prove this theorem is purely automorphic. We count some automorphic representations. So first, two automorphic representations are called initially equivalent if there exists a character of Z to C, so that pi 1 is isomorphic to pi 2 tensor with this initial character. And after Langlands correspondence, we know that we need to count a number of initial equivalent classes of absolutely irreducible classical representations of GLNA. And to calculate this number, we use Arthur's non-invariant trace formula. So we have automorphic spectrum. Here, you need to devise a lattice from the center, but I just write like this for simplicity. And the GA acts by translation, and so the Caspital spectrum lies inside this L2 spectrum. And if you consider the test function given by the characteristic function of the maximal compact subgroup, then this test function acting by convolution should be projection operator. And this projection is until is GO invariant subspace of this L2 spectrum. So its trace on the Caspital spectrum can give you the number of everywhere unramified Caspital representation. And this is our goal. Our goal, more or less, because we want to calculate the number of everywhere unramified absolutely Caspital representations. So there are some difficulties. The first one is, besides Caspital spectrum, there are continuous spectrum and residue spectrum. And the second is, not all Caspital representations are absolutely Caspital. So, but the good news is, first one, we have a very well classification by Langlands and Morgan-Waspuje. The second problem can be solved by Langlands correspondence given by Lohan-Laforgue. So we write always G to be GLN, and we fix a Borel of upper triangular matrices, and we will always write P to be a standard parabolic, and M is the V of P. So Arthur has defined many functions AP AP is the root space, and delta P, phi P, I write they are determined by, I write in the blackboard here. They are determined by a parabolic, by the parabolic P, and they are subsets of this phi ZMG. And we have GAE here. This exists. This has only for function field. Here GAE for integer E. I write GAE to be the RDALS of, so that whose degree of the determinant equals to E. And if you have a parabolic P and you have a discrete representation on this parabolic, I will write a fix. Here P is parabolic and P is a discrete automorphic representation of M, A. And this fix is defined to be the initial characters lambda in XM G. In XM, so that pi tensors lambda is isomorphic to pi. Here XM is just a homomorphism of MA and MA0 to C cross. And the MA0, I write here, consists of those M in MA, so that every factor belongs to the degree 0 part of the corresponding factors. So this is just a set of initial characters. For number field, by looking at the central character of two set, this is just a trivial set. But for function field case, this set is not trivial in general. It depends on pi is absolutely cuspital or not. If it is absolutely cuspital at every component, then this set is trivial. Otherwise, it is not trivial. And we have PM to denote the parabolic, to the set of parabolic subgroups which containing M. And we have a famous function called Arthur's truncated kernel. The definition is long, so I ignore it here. And we have I denote here for the cross-modulus space of Higgs bundles of rank n degree E over X0. So Higgs bundle over X0 is just a pair of vector bundle E and bundle map from E to E tensor omega X0, 1. And it is called, this pair is a Higgs bundle, and it is called stable. If for any F subbundle in E such that theta F is contained in F tensor omega 1, we have the the degree of f, quotient rank of f is smaller than the degree of E and the rank of E. And it is showed by Nietzsche that the cross-moduli space parameterizing stable Higgs bundles exist. And so we consider the text function. The Arthur's non-invariant trace formula is an identity of this form. So here, in the function field case, we need to fix a lattice in the center of GLN. So let A be a degree 1 edel, and the trace formula is defined by this integral. The truncated trace is defined by this integral. And so we want to calculate the geometric side and the spectral side so that we will obtain the information on the number we need. And but because the difficulty of this non-triviality of this set, in the number field case, this set is just empty, but in function field, it's generally non-empty. So we consider a variant. We consider, instead of the integral over all this part, we consider of the truncated function defined by Arthur. We consider this function integral over a small part of a fixing degree part. And because we can do this because this kernel function is invariant by the action of the center of G. And we just have a bijection that GF AZ as a set, as a measure space, this is bijectively to this set. Sorry, here it should be n-1. Due to this decomposition, we have the trace formula, the truncated trace equal to this sum. And instead of calculating every orbital integral and summing them together, we deal directly with Arthur's truncated integral. And so essentially, ingredient for the calculation is the first. Here, the auxiliary T is in the, T is in A, B. And you can think of this as just Rn. And it is a theorem of Arthur in number field case, and then it can be shown easily in the function field case also that this number, depending on T, is quasi-polynomial. I don't define quasi-polynomial, but it's just something looks like a polynomial. In fact, if you restrict to a lattice in this set, then it is a polynomial. And another result, which is essential for us, is a theorem of Low Holophone, that if T is deep enough in the positive Y chamber, then this function defined by Arthur, which is originally very complicated, has a simplification by this. So this part is just a kernel function, and this part is defined by using Harder-Narasimhan filtration of vector bundles. You just need to, because you have a interpretation in function field case, for an l-adic, you can interpret it as a vector bundle. So this function, it just requires that this vector bundle, it means a Harder-Narasimhan filtration, and hence a Harder-Narasimhan polygon. We require that this Harder-Narasimhan polygon is not too concave. It should be dominated by a polygon determined by T. And so this has a very simple form. And so for T large enough, we can deal with this function. And for T small, in fact, for Arthur's trace formula, we need T equals to 0 for GON. So we use the fact that this number depends polynomially on T. And we know how to calculate when T is large enough, then we know what it is for all T. And so the result of the calculation is if I define a vector bundle to be isoclean, if for any decomposition into vector bundles of small rank, we have the mu f equals to mu e. Here, mu is the slope, is defined by this fraction, degree quotient rank. And I denote by Pne x0 to be the number of isomorphic classes of isoclean vector bundles of rank n and degree e on x0. Then I have, for the geometric side, I have this theorem. First, what we want to know is T equals to 0, and E is any number. This is the Arthur's truncated kernel. It equals to the number of isomorphic classes of these vector bundles. And if NE equals to 1, has no common divisor, then we show that this number can also admit another expression in terms of FQ points of Higgs bundles. So in particular, if NE equals to 1, any isoclean vector bundle is automatically indecomposable. So we have, and in fact, geometrically indecomposable. So we have an identity between geometrically indecomposable vector bundles and this number about Higgs bundles. And this is already looks like a variety. So we are done. And in fact, it is calculated by Olivier Schiffmann. Schiffmann has a very explicit formula for this number. And then it was simplified by Mellit, who gives a simpler formula for this number. So using their result, geometric side is done. So we are moving to the spectral side. After Low Holophone, this number we have considered admits a spectral decomposition as a sum. And each sum here, Jp is a parabolic and pi is a discrete representation of the Levy of this parabolic. And you should take some equivalent condition. And so as we want only the information when P equals to G, and pi is absolutely capital. So we want to calculate every term, which is not this case. So first, you need to calculate the weighted, you need to calculate when P is a proper parabolic. In this case, it is a sum of weighted characters. And you need to summing up all these terms. So to give you a feeling what is this expression is, we consider a special case. In this case, trace formula is much more simpler. So we consider a case so that, so you have a parabolic and you have a discrete representation of the levy of this parabolic. You suppose that any two factor of this pi are non-initially equivalent. So I call this set a regular case. In this case, the JP pi E given by Low Holophone following more or less Arthur's method has this expression. The first, it is a sum over the set I have defined here. And then it is an integral over the group of initial characters. It is in fact a Lie group, and we take it is an imaginary part. So this is a compact Lie group now. It is but not, this group is not, in general, not connected, but we can still consider integral over it. And this part, this function I will explain later. And this part is the intertwining operators from P to Q. We take intertwine from P to Q and we take it back. And this operator is just a twisting operator by a character. So about this function are some rational functions on this Lie group. And they have the following properties. The first one is that this product is a regular function on XMG. The second is that this limit is always convergent due to the functional equations of intertwining operators. And Arthur has developed a method called GM families to deal with this kind of sum and limit. And this is the so-called weighted characters. So so first of all, we have intertwining operators, but because we consider only everywhere unramified representations, so this operator, and this, for any representation, this space, it is well known that for any representation, this GO has dimension 0 or 1 if pi is everywhere unramified. it is 0, if not else. So the test function we choose already killed this case. So we consider this case, this is a one-dimensional space, and hence this intertwining operator should act as scalars. And these scalars is just normalization scalars for intertwining operators. They are very explicit in terms of Rankin-Selberg L functions. And there is a small twisting character here. In fact, we show that this twisting character always act as, by taking trace, act as an identity. So now we know almost everything here, except how to calculate this limit. And this is shown in number field case by Arthur. In number field case, Arthur has calculated these limits explicitly. And we prove that because we have, in the beginning, we have choose a degree E. We prove that when E and N are coprime, then Arthur's result, in fact, holds in our case too. So this is somewhat following Arthur, but needs some small modification in function field case. If this lambda pi is not in XGG, then this integral is 0. And if this lambda pi is in XGG, then this limit equals to this sum. The first one you can ignore, it's not important. The essential one is this one. And first you take a sum over all subsets F of negative roots associated to P, so that F forms a basis of the root space. And then you consider the product of all of this beta in roots in F, and so that we consider two operators. The first is the operator which takes the number of zeros. The second is take the number of poles. And this n beta is just this function. This is well known. And so we need to know the number of zeros and number of poles in this region. And this can be known by the work of a series of people. First, by Laurent-Laforgue, we can move to geometric side to know the L function of some local systems. And then by work of Lomon, we know functional equations. And using functional equations, we can know about the number of zeros and the poles of this function. Of course, we also use the fact that these L functions, sometimes it has poles, sometimes not. This is well known. And continue to the calculation. So now this is somewhat a result of Arthur, but it's still not so explicit, especially the first sum. The first sum, you take subset of phi p, but you don't know when this is a basis, forms a basis of this vector space. So to solve this, we use graph theory. And I consider, so we can come into the elementary world. I consider this vector space, and I define a set phi to be ei minus ej for all I smaller than j. And if you have a subset of phi of cardinality R minus 1. I want to know when f is linearly independent. So to consider this, I can draw a graph f so that the set of vertex of f are just 1 to the r. And the edges are those ij. If you have a vector ei minus ej in f, you can draw an edge from I to j. And in this way, you obtain a graph. And the proposition is that f is linearly independent if and only if this graph is a tree. It is a tree means it is connected and there is no cycle in f. And there is a theorem of Chikhanov. This theorem tells you how to calculate this sum. So if you have a family of complex numbers and you have a matrix, a symmetric matrix, so that for its upper triangular elements, they are y ei minus ej. And for the diagonal, I take in such a way that the sum of elements of every line is 0. And hence every column is 0 too, because it is symmetric. And then Chikhanov's theorem is about generating functions of trees. When you use his theorem, you obtain this identity. The left-hand side, it is exactly the form of Arthur's calculation. The right-hand side is just, you have a matrix, you can consider the cofactor of this matrix. And you know, it is a theorem that these cofactors are all the same. So you can take any cofactors. So now you can express this sum in terms of determinant. So you need to calculate this determinant when our discrete pair is so that the pi are all capital. This seems to be not difficult to obtain. But if it is, if some factors are residue, then the calculation of this determinant is still difficult, but it can be done. And so I tell you the result. Finally, after all the calculation about the spectral side, you can write the spectral side as a very complicated function. The first, I define a function which encodes the information of the number we are looking for. And I define an operator which takes the coefficients of corresponding to ZV. And so you have this expression. Here, U is the Mobius function. And others are, but this has the advantage of being a purely combinatorial functions. So using, yes. As though it is complicated, you know, it is this form, JE, when, of course, EN is equal to 1. You know, this is the number you want, CN1, plus other terms. And these other terms only is about CMK, so that the M is smaller than N. So I already know that this is a good number. It is a linear combination of Q-way numbers. So this is good. To show this is good, you can use induction. And after induction, we proved our main theorem. And so that's my talk. Thank you.
I would like to say a few words about the geometric side, about why the number of parts of the
Yes. Yes. Yeah. So you mean the second identity? The second identity, in fact, most of work are done by my advisor. So I want to do this using somewhat Hitchens fibrations, and you have this is a geometric side of trace formula, and you can define a similar of geometric side of trace formula for Lie algebra. And this gives you somewhat, this is just exactly the right-hand side. This is right-hand side. You can, using Hitchens fibration, you can write this as a sum over Chi's characteristic polynomials, right? So it is just in FQX, and you define a similar expression. This expression gives you more or less the number of points on each fibers. Yeah. On this side, I can do the same thing. The characteristic polynomials in FQX, but you need that the constant term of this polynomial is non-zero, right? Is somewhat a group version. Yeah. So you define the similar one. And I show that this one equals to this one when this chi equals to this chi. And for others, there's some, for example, when A0, yeah, here, there are A0 equal to 0 case. And yeah, when En equals to 1, show that this, when A0 equals to 1, this expression gives the nilpotent, so it is independent of, so somewhat you obtain the result.